In this lesson, we're going to take a look at the conservation of energy, specifically looking at gravitational potential energy in a different form than we've looked at before. Before, it relied on gravitational acceleration being a constant. And what we want to do is look at that here now that we know that that's not entirely true. So when we said gravitational potential energy was equal to mgh, we assumed that g was a constant everywhere as it moved. But g is not actually constant, right? Especially not when you're talking about, something orbiting something else. And so that ends up being a little bit of an issue. Also, h was set at an arbitrary reference point. Remember, we could always call zero gravitational potential energy wherever we wanted, and it was all relative to that. But those two things don't really work anymore. We want to think about, where would gravitational potential energy be zero now? Well, it turns out it's not at sort of like the bottom or on the surface of the Earth. That doesn't really work for us. So we need a reference point that works for every possible situation. And calling it the center of the Earth makes the Earth the reference point for everything, and that doesn't really work. So what we end up doing is we pick a point that it is infinitely far away from everything. We'll come back to that. So here's our situation. We start with our standard form. If you call h0 at the ceiling, as you move your mass down, gravitational potential energy gets more negative. As you move it up, it gets less negative. So the change in potential energy is positive if you lift it up and negative if you lower it down. And so what this means, practically speaking, for the person holding the box, is that everywhere in this room, gravitational potential energy is negative, but a change in gravitational potential energy is positive if you lift it and negative if you lower it. So what we're going to do to kind of mimic that situation is we're going to let gravitational potential energy be zero when something is infinitely far away. So what does that mean? It means if I were to take something like my water bottle and lift it up off the surface of the Earth and keep taking it further and further away until it was infinitely far away, at that point, the gravitational potential energy between the bottle and the Earth involved in that system would be zero. And that means everywhere else it's negative. This actually works really well, and we'll see this more when we get into electricity, how this kind of mirrors what happens there. Basically, we describe this as living in a gravity well, where to get up to the surface, out of the well, you have to go infinitely far away. And the closer you get to the object, the further down the well you are. And that's the idea. So close to massive objects, down into the well. More negative. To get out of the well, you have to go infinitely far away. To do, as you go out further away, you're doing positive work, as it would be to lift something up. So in that way, it is consistent with what we already know, which is important. So what are we going to use to derive this? What mathematical relationship? Because mgh isn't going to work. So let's think about this. The form that you see on your equation sheet is that gravitational potential energy is negative gmm over r. So in other words, it depends on how far apart you are or how far up you are from the surface of some planet or from the center of some planet. And then it depends on the masses involved. It's got a lot of similarities to the gravitational force. And that's because, of course, just like we said with gravitational potential energy before, there is a relationship between the conservative force and the potential energy. So the units check out nicely. We end up with joules, so we're good there. Let's think about how we derived the old version of gravitational potential energy. You do work to lift up a box at constant speed, and that work is equal to your applied force dr integrated. And that applied force is equal to the weight of the object. So that's mgh. Or the change in potential energy is the work done to lift it up, so that's how much energy was stored. Now, if we think about a new version, we place some mass, a distance r from the center of another big mass, capital M, and we're going to lift it up or pull it away to infinity. That requires work, right? Because there is a force attracting those two masses together. So to move it away, you have to apply a force. So the work is still the same thing, the integral of f dot dr. The big difference is the force is not a constant as it was before, right? They are equal, these two forces, the force of gravity and the applied force, for the sake of moving at constant speed. But now we're integrating from r, where we start, to infinity, gmm over r squared with respect to r, because that is the formula for the force of gravity. If we do this integration using the power rule, We solve, we end up with negative GMM over infinity. Well, whenever you divide by infinity, it goes to 0 essentially, plus this other part. So we end up with a positive GMM over R. So that's the gravitational potential energy change to lift from some distance R to infinity. And there's a subtlety here we need to figure out. Well, that's the gravitational potential energy to lift up. So then how much gravitational potential energy did we have when we weren't at infinity? Well, it's negative GMM over R, because that plus GMM over R, the change, gets us to 0 at infinity. And that's where that formula comes from. Now, there's important pieces to this. The first is it's basically proportional to 1 over R, not 1 over R squared. So that's the way it differs from the force of gravity. And it is always negative, except at infinity. And so this gravitational potential energy is about two masses. How much energy is stored in placing two masses near each other? The work required to pull them apart is positive GMM over R, and the energy stored by them being near each other is negative GMM over R. So here's an example of how we might use this. So you have an object at altitude of 2r Earth, and then it falls to the Earth. What is the final velocity? Well, we can't use kinematics equations because g is not a constant equation, constant value. We must use conservation of energy. So what do we have? Well, we have our conservation of energy formula. The kinetic energy initial is gone, but we start with gravitational potential energy of negative GMM over 3RE because we are a distance 3 Earth radii from the center of the Earth. Our final gravitational potential energy is over RE because that's what we're at the surface. And then we have 1/2 mv squared, the kinetic energy term in the middle. The mass of the object falling cancels out. We do some rearranging, and we end up with the square root of this mess, which we can plug in the values to get 9,000 meters per second, which, right, not necessarily a number that makes a ton of sense, but if you drop it from a very high height, you would expect it to be moving very fast. Now, of course, there's no non-conservative forces here, no friction, no air resistance. Another example would be what happens if we have more than one object in the universe, right? Our previous formula was all about the system being just two masses. But if you have more than two masses, you need to be a little bit more careful. And here's how we do it. Well, the gravitational potential energy of mass 1 that it has for being in that position has to do with it being near 2 and near 3. So we need to do a couple of calculations. The gravitational potential energy stored, or that it is there by placing 1 there, is its gravitational potential in relationship to 2 and in relationship to 3, which we can calculate individually and combine together. What about the gravitational potential energy of the whole arrangement? Well, you have to sort of scalar sum these pairwise. You have to think, well, if 3 was there first, and then I brought in 2, some energy was stored. And then I bring in 1, and I store more energy. And so that's the way we need to think about this in order to understand what's going on with gravitational potential energy storage. So here's how it goes. The total gravitational potential energy stored is the sum of the gravitational potential energies stored for each individual action. The pair of 1 and 2, of 1 and 3, and of 2 and 3 combined together is the total amount of energy stored. And this is the work done to assemble the whole arrangement. The last thing I want to look at, not the last thing, but one other thing I want to look at is this concept of escape velocity. If you were to graph the gravitational potential energy for some mass near the Earth, it would look like this, right? The further out you get, the closer to 0, but it's this curve. So gravitational potential energy is always negative. How can we escape? Well, what we need is we need enough energy to climb out of this well to infinitely far away. Basically, when we get to this point, I want to be at rest, infinitely far away. That's our condition. We need enough kinetic energy so that when we get out to gravitational potential energy is 0, all of our kinetic energy has been used up. So that's the way this is going to work. We have 1/2 mv escape velocity squared minus GMM over the radius of the Earth, because that's what we had at the beginning. Cancel out that m, do a little rearranging here, and you end up with about 11,000 meters per second, which is not really that fast, right? I mean, it is pretty fast, but it's not impossible to reach that velocity. So a couple things to notice. For any circular orbit, the escape velocity is square root of 2 gm over r, which is root 2 times its orbital velocity. As long as v equals v escape, it doesn't matter, right? You could head off tangent straight out. It doesn't matter. The path you take to get there would matter, but that's okay. In this case, we escape the Earth, but you'd still be trapped around the sun. So you'd have to think about that one as well. All right, that's our conservation of energy for orbital motion bit. Hope that makes some sense, and we'll talk more about that later.